The next section is about planes in general and understanding planes. And the most basic kind of problem in such a situation is if you've got 3 points that are not all on the same line, 3 separate points in space, they're going to determine a plane. How do you describe that plane? Say the 3 points have coordinates P, Q, and R. Maybe P has coordinates -2, 2, -5, -3. Q has coordinates 1, 4, 2, and R has coordinates -5, 3, 4. I pick those numbers somewhat randomly. When I pick such numbers somewhat randomly, in all likelihood, they're not on the same line. Have to be very unlucky for these to all be on the same line. So I'm trusting they're not all on the same line. The basic idea of how to determine and to describe the plane that these points are in, they determine a plane, is to figure out a couple displacement vectors, say from P to R and P to Q, and determine a vector perpendicular to this plane using those 2 vectors. Take their cross product. Call this vector V and this vector W. Cross product with the right-hand rule is going to be a vector like this. Perpendicular to both of them and therefore perpendicular to the plane. It should seem useful that finding a vector perpendicular to the plane might be helpful in describing the plane. And yes, that's the case. That's the key idea. Such a vector is often called a normal vector and denoted by the letter N. Normal vector to the plane. So we want to find N. But first we got to figure out V and W if we know P, Q, and R. V is going to be the displacement vector from P to Q. Take the coordinates of Q and subtract the corresponding coordinates of P. 1 minus 2 is -1. 4 minus -5 is -9. 2 minus -3 is -5. They're all negative. Did I make a mistake? Look good? Then I do 1 minus 2, 4 minus -5, and 2 minus -3. I'm going from P to Q. I have to take the coordinates of Q and subtract the coordinates of P. That's the way to do that. Oh, okay. All right. Thank you. 2 minus -3. For some reason, I don't know what in the world I was thinking. Okay, thank you. W goes from P to R. Hopefully I don't make a mistake this time. -5 minus 1 is -6. 3 minus 4 is -1. 4 minus 2 is 2. Okay, that seemed easier. Okay, so these are my 2 V and W's. Now I want to compute the normal vector to the plane, V cross W. The normal vector is not unique. Any scalar multiple of the normal vector, any non-zero scalar multiple, will be another normal vector. So you got to use your cross product techniques to find that cross product. For the sake of time, we'll just have Mathematica do it. Mathematica can figure out cross products very rapidly. Just to show you that it can be done, let's go ahead, plug in P, Q, and R to start. P having coordinates 2, -5, -3. Q, 1, 4, 2. R, -5, 3, 4. V effectively is Q minus P, and W is R minus P. We have the correct V, yep, and the correct W. There they are. Oh, no, not the correct W. What in the world? Today's not my day. I subtracted Q. I wanted to subtract P. It actually would have worked to subtract Q as well. It'd just be a different vector. But I want to do P to R, so it's -5 minus 2 is -7. 3 minus -5 is 3 plus 5 is 8. 4 minus -3 is +7. Is that what I got? Yep, -7, 8, 7. Okay, the quick way to do cross product in Mathematica is cross become a W. There it is. There's N having components 23, negative 28, 55. How does this normal vector to the plane determine the plane? Think of it this way. If you got an arbitrary point in the plane, so here's your plane again, you got an arbitrary point with arbitrary coordinates x, y, z, and you got a particular point like our point P, that means an arbitrary vector parallel to the plane, lying in the plane if you put its initial point at P, will look like that and be orthogonal to N. The dot product of this vector with N will be 0. And since the point x, y, z is arbitrary, that'll give us a general condition for the point x, y, z to be in the plane. So N dotted with, better write it as a vector whose first component is x minus the first component of P. The first component of P, you can see in Mathematica, was 2, comma y minus the second component of P. Y minus negative 5 is y plus 5. Comma z minus the third component of P, which is negative 3. Z minus negative 3 is z plus 3. And this has to equal 0, the number 0, where again, N is 23, negative 28, 55. Computing this dot product then gives a scalar equation, 23 times x minus 2 minus 28 times y plus 5 plus 55 times z plus 3 equals 0. A scalar equation involving the three unknowns x, y, and z. And that'll be an equation for the plane. That form of the equation is called standard form. It's using the normal vector and an arbitrary vector parallel to the plane and saying, hey, their dot product has to be 0. And since it's an arbitrary vector parallel to the plane, it gives you a general equation that completely describes the plane. There's also something called general form found by simplifying this effectively. Multiply it all out. Like this. And then in standard form, we typically bring all the constants to the other side. And write 23x minus 28y plus 55z equals, bring the constants to the other side, 46 plus 140 minus 165. That's 186. So this simplifies to 21. 23x minus 28y plus 55z equals 21. That's the general form. The standard form always has 0 on one side. The general form may or may not have 0 on one side. If it does have 0 on one side, that means the plane goes to the origin, because x, y, z all equaling 0 would solve it. If it doesn't have 0 on one side, as this one doesn't, then it does not go to the origin. 0, 0, 0 does not satisfy this equation. Picking random points P, Q, and R is going to typically result in a plane that does not go to the origin. Let's use Mathematica to see if this seems right. Probably do this code and just modify it here. With the contour plot, I'm only plotting one plane this time, not 3 planes. Let's do the general form. 23x minus 28y plus 55z You need double equal signs. Don't do a single equal signs. It'll mess everything up when using contour plot or contour plot 3D. So that'll plot the plane. I've also got the axes in there. I don't want to use parametric plot anymore because I'm not drawing a curve or a line. I am plotting 3 points though, P, Q, and R, in fact. So we should see a plane with these 3 points in the plane, hopefully. And we do. If you move it around, it does look like those points are in the plane.